primary purpose of a supplemental made electrode with ground rods placed on a charcoal bed is to enhance the grounding system's overall performance and reliability. The charcoal bed provides a large surface area for the ground rods to make contact with the soil. This increases the points of contact and reduces the resistance to ground. Charcoal is a good conductor of electricity and helps to facilitate the flow of electric current from the ground rods into the soil. Charcoal has the ability to absorb and retain moisture from the soil, and this ensures continuous conductivity even during dry conditions. The supplemental electrode provides an additional path for electrical current to flow to ground, improving the overall reliability of the grounding system. By providing an effective grounding path, the system helps to reduce the risk of electric shock to personnel in the vicinity of the electrical equipment. A proper grounding system helps to protect electrical equipment from damage due to lightning strikes or other electrical faults. The specification may have included this requirement for the following reasons. Firstly, the soil at the project site may have poor conductivity, making it necessary to supplement the water pipe ground with an additional electrode. Secondly, some local codes or industry standards may require additional grounding measures for commercial projects. Thirdly, certain electrical equipment may require specific grounding system configuration to ensure proper operation and safety. The number and spacing of the ground rods will depend on the size of the project and the soil conditions. Charcoal should be of high quality and free of impurities. The bed should be at least 3 inches deep. The supplemental electrode should be bonded to the water pipe ground, building steel, and rebar in the foundation to create a comprehensive grounding system. The installation of ground rods in a charcoal bed serves several important functions within an electrical grounding system. It primarily aims to improve the conductivity and overall effectiveness of the grounding system, especially in environments where soil conditions are not ideal. The enhanced grounding system is crucial for safety and equipment protection. Ground rods are typically made of copper or copper-clad steel, and they act as the primary interface between the electrical system and the earth. Their purpose is to provide a low resistance path for fault currents to dissipate into the ground. The depth and number of ground rods installed are determined by local electrical codes and the specific requirements of the installation. In many regions, codes specify a minimum depth and resistance value that must be achieved. The resistance to ground is a critical factor. A lower resistance indicates a more effective grounding system, allowing fault currents to flow more easily and quickly, thereby minimizing the risk of electrical shock and equipment damage. Soil conditions such as high resistivity, dryness, or rocky terrain can significantly impede the effectiveness of ground rods. In such cases, supplemental measures are necessary to reduce the ground resistance. This is where the charcoal bed comes into play. The use of a charcoal bed around ground rods is a technique designed to enhance the conductivity of the soil immediately surrounding the rods. Charcoal is highly conductive and porous, allowing it to retain moisture and improve the electrical contact between the ground rod and the earth. The charcoal bed helps to maintain a stable and low resistance connection, even when the surrounding soil dries out or has poor conductivity. The installation process involves excavating around the ground rods and creating a bed of charcoal, typically about 3 inches or more in depth. The ground rods are then placed within this charcoal bed, ensuring good contact. The charcoal used should be of a high quality, low ash variety to prevent any potential corrosion or degradation of the ground rods over time. The benefits of using a charcoal bed are multifaceted. Firstly, it improves the electrical conductivity of the soil, reducing the overall ground resistance. Secondly, it enhances moisture retention, ensuring a more stable grounding system in varying weather conditions. Thirdly, it helps to distribute fault currents more evenly, reducing the risk of localized voltage gradients and step potentials, which can pose a safety hazard. Another important aspect of the grounding system is the bonding of various metallic components. Bonding refers to the practice of connecting all non-current carrying metal parts of an electrical system to create a common ground. This includes items such as metal water pipes, building steel, and the rebar and concrete foundations. By bonding these components together, the electrical potential is equalized, reducing the risk of voltage differences that could cause electric shock. The main purpose of bonding is to provide a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices such as circuit breakers or fuses to quickly trip and energize the circuit. This is critical for safety and preventing equipment damage during a fault condition. In addition to bonding, grounding and surge protection are essential components of a comprehensive electrical safety strategy. Grounding provides a reference point for the electrical system, ensuring that all circuits are at or near ground potential. Surge protection devices, such as surge suppressors, are designed to protect sensitive electronic equipment from voltage spikes caused by lightning strikes or power surges. These devices divert excess voltage to ground, preventing damage to the equipment. Grounding and bonding must comply with local electrical codes and standards. These codes provide detailed requirements for the installation and maintenance of grounding systems to ensure safety and reliability. Regular inspections and testing of grounding systems are essential to verify their effectiveness and identify any potential issues. Ground resistance testing is a common method used to measure the resistance of the grounding system. This test involves injecting a small current into the ground and measuring the resulting voltage drop to calculate the resistance. If the measured resistance exceeds the maximum allowable value specified by the electrical code, corrective actions must be taken to improve the grounding system. In summary, installing ground rods in a charcoal bed is a technique used to enhance the conductivity and effectiveness of electrical grounding systems, especially in areas with poor soil conditions. It improves conductivity, enhances moisture retention, and helps distribute fault currents evenly. Bonding, grounding, and surge protection are integral parts of a comprehensive electrical safety strategy, ensuring the safety of personnel and the protection of equipment from electrical faults and voltage surges. The specifics of grounding and bonding can be found in the National Electrical Code, or NEC. The NEC provides detailed requirements for grounding electrode systems in Article 250. Grounding electrode systems serve to connect the electrical system to the earth, providing a path for fault current to return to the source. The primary grounding electrode is often a metal underground water pipe. The metal water pipe must be in direct contact with the earth for at least 10 feet or 3.0 meters. This provides a reliable connection to ground. However, the NEC requires that the metal water pipe be supplemented by an additional grounding electrode. This is to ensure that the grounding system remains effective even if the water pipe is disconnected or becomes non-conductive. Acceptable supplemental grounding electrodes include ground rods, ground plates, and concrete encased electrodes, often referred to as UFA grounds. Ground rods must be at least 8 feet, or 2.4 meters, in length and must be driven into the ground. Ground plates must have a surface area of at least 2 square feet, or 0.19 square meters, and must be buried below the permanent moisture level. Concrete encased electrodes must be at least 20 feet, or 6.1 meters, in length and must be encased in at least 2 inches, or 50 millimeters, of concrete. The NEC also specifies requirements for the size of the grounding electrode conductor. The grounding electrode conductor connects the grounding electrode to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. For example, if the service entrance conductors are 4/0 American wire gauge copper or 250 kc mil aluminum, the grounding electrode conductor must be at least number 2 American wire gauge copper or number 1/0 American wire gauge aluminum. The NEC also provides requirements for bonding. Bonding is the connection of all non-current carrying metal parts to the grounding system. This includes metal conduits, metal enclosures, and metal equipment. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The NEC specifies that bonding jumpers must be used to connect metal parts to the grounding system. Bonding jumpers must be sized according to the size of the circuit conductors. For example, if the circuit conductors are number 10 American wire gauge copper, the bonding jumper must be at least number 12 American wire gauge copper. The NEC also provides requirements for equipment grounding. Equipment grounding is the connection of the non-current carrying metal parts of electrical equipment to the grounding system. This includes appliances, motors, and other electrical devices. Equipment grounding ensures that the metal parts of equipment are at the same electrical potential as the grounding system, reducing the risk of electric shock. The NEC specifies that equipment grounding conductors must be used to connect equipment to the grounding system. Equipment grounding conductors must be sized according to the size of the circuit conductors. For example, if the circuit conductors are number 12 American wire gauge copper, the equipment grounding conductor must be at least number 12 American wire gauge copper. In addition to the NEC, other codes and standards may apply to grounding and bonding. These include local built-in codes, industry standards, and equipment manufacturer specifications. It is important to consult all applicable codes and standards when designing and installing a grounding and bonding system. Proper grounding and bonding are essential for electrical safety. They help to protect people from electric shock and prevent damage to equipment. It is important to understand the requirements of the NEC and other applicable codes and standards when working with electrical systems. A supplemental grounding electrode, especially one incorporating a charcoal bed, addresses specific challenges in achieving effective grounding. The primary goal of any grounding system is to provide a low impedance path for fault currents to return to the source, thereby facilitating the quick operation of overcurrent protective devices such as circuit breakers or fuses. This rapid response is critical for preventing electrical shock hazards and minimizing equipment damage. Several factors can influence the effectiveness of a grounding system, including soil resistivity, moisture content, and the contact area between the grounding electrode and the earth. High soil resistivity, which is common in dry, sandy, or rocky soils, significantly increases the impedance of the grounding path, making it more difficult for fault currents to flow. Insufficient moisture content exacerbates this issue, as water is a good conductor of electricity and helps to reduce soil resistivity. The contact area between the grounding electrode and the earth is also crucial. A larger contact area provides more pathways for current to flow, thereby reducing the overall impedance. A supplemental grounding electrode is used to overcome these limitations. By installing additional ground rods, the overall contact area with the earth is increased, providing more avenues for fault current dissipation. Charcoal bed further enhances this effect by improving the conductivity of the soil immediately surrounding the ground rods. Charcoal is a highly porous material that can retain moisture even in dry conditions. This helps to maintain a stable and low resistance connection between the ground rods and the earth, regardless of fluctuations in soil moisture content. Moreover, charcoal is a good conductor of electricity, which further reduces the impedance of the grounding path. The installation of a charcoal bed typically involves excavating the soil around the ground rods and replacing it with a layer of charcoal. The charcoal should be of a high quality, low ash variety to prevent any potential corrosion of the ground rods. The depth of the charcoal bed can vary, but it is generally recommended to be at least 3 inches to provide adequate coverage and conductivity. In addition to improving conductivity and moisture retention, a charcoal bed can also help to reduce soil corrosion. Certain types of soil can be corrosive to metal, which can degrade the ground rods over time and compromise the effectiveness of the grounding system. Charcoal acts as a barrier between the ground rods and the corrosive soil, helping to extend the lifespan of the grounding system. When designing a supplemental grounding system with a charcoal bed, it is important to consider several factors, including the size and spacing of the ground rods, the depth and extent of the charcoal bed, and the overall soil conditions. The size and spacing of the ground rods should be determined based on the specific requirements of the installation and the recommendations of a qualified electrical engineer. The depth and extent of the charcoal bed should be sufficient to provide adequate coverage and conductivity, taking into account the soil resistivity and moisture content. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. Ground resistance testing should be performed periodically to verify that the impedance of the grounding path remains within acceptable limits. Visual inspection should also be conducted to check for any signs of corrosion or damage to the ground rods or charcoal bed. In summary, a supplemental grounding electrode with a charcoal bed is a valuable tool for enhancing the effectiveness and reliability of electrical grounding systems, particularly in challenging soil conditions. By improving conductivity, moisture retention, and corrosion resistance, it helps to ensure the safety of personnel and the protection of equipment from electrical faults. The information presented here is for general guidance only and should not be considered a substitute for professional electrical engineering advice. Always consult with a qualified electrical engineer or electrician when designing or installing electrical systems.